world in 3D. Okay? But the world, there are more dimensions. But we cannot perceive them. So, in a computer world, while computers are powerful, they can actually perceive even 4D world. Alright? So it will move like this, and then it will move like this. Okay? And then it can move like that. Alright? There. If there's another dimension, it will move in that dimension. So another dimension could just be another X, Y, Z. So it will move along that, it will move along that, it will move along that, it will move along that. Okay.
Multi-dimensional.
I don't like this pen. Right. So the role of a kernel. A kernel is a filter. The kernel could be
Yes.
a kernel is a filter. Filters are very popular in signal processing.
Filters.
Most filters are applied in the frequency domain. When you have a signal that is the perfect cosine or sine, it has the amplitude, then it has what? What is this?
Yes.
Wavelength, right? Wavelength, right? Is there another one?
P.
So this will be a cosine of x, I guess, or a sine of x. Say again. Now, if I combine this signal with another one that goes like this, it will also have the amplitude, it will also have the wavelength, but it will be shifted a bit. Okay? If I combine it with something like this, I have three signals. Okay? If I convert them each into the frequency domain, the first signal will have 1 over the wavelength, isn't it? The frequency. What is the frequency for this? Say again? 1 over time. Okay, so the time it takes to cover 1 over 1 wavelength. Okay? Yes. Now, for each one from 0 to, they will have different frequencies. So if I combine them, I take this one and that one and this one at 0, they will give me a certain value. I combine them here, they will give me a certain value. This will be double that divided by that. It will come back maybe right here, and so on and so forth. So this signal could go something like that, or whatever the case may be. So it means if the wavelengths of all of these are different, okay? The wavelengths is that they are different. The time it takes for each one of them to cover one wavelength is different, okay? That means each one of these signals is propagating at a different frequency. Again, the other one is oscillating quickly, the other one is oscillating slowly. Again, the wavelength tells you that. So if I combine them, I could probably get something that could go like this. Alright? And if I take this and do Fourier transform of, let's say this is f of x. In the frequency domain, I'll get multiple frequencies. I'll get each one of these frequencies. Okay? So I'll get 1 over t for the first cosine. It will be something like this. The delta Dirac will give me a point there. And then the other one, the third one, it might give me something like that. Fourth one might give me something like that. It means this signal has 3 frequency components. Okay? I'm just doing a simple, straightforward signal processing. Alright?
Yes.
1D convolution, we can process this signal, okay, using 1D convolution again, because we can be able to sample it at different. It could be the stop. One of these could be the stop, or this one. This could be the stop. Again, it could be the stop price. Again, kapag kami makakata ha, mana hai? Jangan mula hapon. Again, at different times of the year, over longer period. But they will become a pattern of okay, null teaching. So filters are easier to apply in the frequency domain because we can simply say, get me a filter U, which is our tenor, okay? And define it as a step function that will be 0 everywhere and be 1 here, okay? And so, because when we filter, we do a convolution, u of x of f of x, because it's 0 everywhere, it is 1 here, it will only take, it will give me this frequency f2, okay? Because we are multiplying. So if it's 0 everywhere, it's 1 here, that means this frequency will come out at the end. So if this multiplied by the filter, it will be 0. This one will be cancelled, this one will be cancelled. 1 multiplied by this, I'm left with f2. That's how the filter works. Does that make sense? Okay? In the frequency domain. Alright? How about the moment CDFM, which not to the frequency of CDFM? This is exactly what you are doing. Okay? The CDFM is 91, 88.1 megahertz. This, this. So one over time you are actually getting the frequency. This is not megahertz. Okay? We are talking about electromagnetic waves. Yes, that's this. This is exactly what they are doing. We are doing filtering in the time domain. Okay? We are doing filtering in the time domain. So the kernel, what are we trying to explain? This. We're trying to explain what the kernel does. It does this exact operation in the time domain. Okay? Alright. So the kernel, what is a kernel in a convolution? So in our slides, if you go to the slides where we explain the kernel is a matrix, is a vector. That gives us the features of our input. It extracts the features of our input. Okay? So in this particular case, these are the features of our signal. It has these frequencies. This is how you can describe it. Okay? I just maybe went over, but it's just easier to explain the frequencies. Okay? Idea? So a kernel is a small matrix of weights used to scan across the input and detect specific features.
Awesome.
So in our image, the one we had in the slides, we had something like this, and our feature, our kernel had something like this. So we had something like this. Okay. In this example, we said our kernel or our filter is a stepwise function that is 0 everywhere and 1 at f of 2. In other words, it is 1 at f of 2, at that frequency. It means it will always come up with any frequency. Or at this point, f of 2 minus half, f of 2 plus half. So if it's 1 all here, where x f of 2 divided by 2 minus so f of 2 minus half. Alright? So in this particular case, in the 2D, we have that, and then if you move this here, and like that, when it gets to this point, it will extract the feature. Do you still remember that slide?
Yes.
Okay. So that is our kernel. How does the size of the kernel affect the feature extraction process? Any takers? So the answer is not necessarily in the slide, but a small kernel will be very specific. It will choose very specific features. Okay, the larger kernel will have a more general or it will detect boundaries within the picture. All right. So if you had a smaller edge like this one, it will detect maybe small edge. If you have a bigger one, it will detect that entire thing. All right. Okay. Now, what are feature maps?
Feature
You can look at slides 8 and 19.
Slide 90. 18, 19.
Yes. What are feature maps? What are feature maps? Is the output of the filter map? Okay? It gives you a map of the features that are available. Okay? If you apply this filter, it's telling you that we have that feature. Okay? This signal has this frequency. Okay? If we apply this filter here and there was no delta direct there, we will get a 0, right? It means there's nothing there. So there will be no feature map. Okay? If you apply the filter and it comes up with an output, then it tells you this picture has certain feature. This picture has this feature. So the feature map is actually whatever was in the kernel. It's in the kernel. It says I'm the kernel. I'm gonna search if I'm available. And if I am available, then I'm your feature. Okay? If I applied a kernel that looks like this on this one, we'll get nothing. Okay, we get a very low value. Okay? So that means we don't have a feature like that in that particular picture. Okay? Oh. All right. Okay. So let's talk about generalization. We can skip the locality of convolution. In 2D convolution formula, okay, they explain in words what the summations are doing.
2D convolution formula.
Yeah, get an example. But the answer is actually in slide 27. So remember, when you're moving the kernel, you are multiplying at a specific point. Okay? If you look at that, it says it's doing component-wise. It looks at this point, it looks at also at that on the other point, it looks at that, and then it sums. So that at this precision, the kernel looks at a small version of the input, okay, just the patch, multiplied place the corresponding medicine at the marker, yeah? So it's kind of a local processing.